right. Now that I'm all mic'd up, I'd like to thank the organizers for inviting me to participate in this really interesting conference. And I want to acknowledge my somewhat large and multi-organizational and interdisciplinary co-authorship team. It takes a village to do this kind of research. Okay, so I'm going to press this button. Oh, there we go. Okay. This is an exciting time to be working on AI. Even as AI technology advances, our ability to measure its economic impact at the firm level is also advancing rapidly thanks to creative and informative research efforts led by many in this room and many outside of it. A valuable effort to directly survey AI use by U.S. firms has been co-authored by some of my own census-based co-authors. The exciting and influential work of Tanya Babina and her co-authors have used data on the hiring of AI workers as reflected in online job data to gain new empirical measures of the impact of investment in and use of AI. And we've learned much from both efforts, but unfortunately neither of these papers has provided strong evidence of the kind of productivity boost we're hoping to eventually receive from the AI revolution. Now, more recent experimental evidence provided by Eric Brynjolfsson, Daniel Lee, Lindsay Raymond, and others provides compelling evidence of AI-generated productivity gains, but we don't yet know whether and how these productivity results generalize beyond the very specific work contexts in which they're documented. So we think that this paper provides a useful complement to these existing streams of literature. We build on and extend recent efforts to identify AI-related patents, and then we match these data to the inventing firms in the U.S. Census Bureau microdata, and we find evidence consistent with positive and significant effects of AI invention on productivity, especially labor productivity, within the AI inventing firms, and also positive impacts on employment with those AI inventing firms. And this comes from a sample of firms that it's distributed across industries, technologies, and geographies, giving us the kind of broad-based productivity boost that we've been looking for in the data. Right? We also, in this paper, examine ongoing efforts to quantify the impact of elite academic scientists on AI-related invention through direct collaboration with firms and through the employment of their doctoral students in these firms. This work is more preliminary, but we'd love to get the reaction of this audience to that work. All right. So, given our time constraints, I don't really have the time to delve too deeply into our somewhat complicated methodology for identifying AI-related patents. The details are in the paper. I'll just say this: we use AI to find AI-related patents granted by the USPTO. So like many of these exercises, we start with a previously identified hand-curated set of AI patents. And then we train a support vector machine to identify more AI and non-AI patents with some human input. So we have human experts confirm the high confidence cases and manually label the borderline cases. And then we train several different ML models on the expanded training data set. And then we compare the outputs of these different models and we identify high discrepancy patents, and we use that as a challenge data set on which to train our models. And we bring all these models together into an ensemble, and we essentially predict the AI-ness of every US patent granted between 1990 and 2018. And over the summer, we've been working to update these data all the way to mid-year 2024. Okay? Now, we're not the first researchers to attempt this. Ian Coburn and his co-authors and Mike Webb and his group have done this, focusing on a small set of keywords and phrases and particular patent classes, right? Because our method uses the entire text of the patent and doesn't rely on a small set of keywords and phrases. We find far, far more AI-related patents than this previous work does. However, we have to concede that the USPTO has also tried to use machine learning methods to identify AI patents, and they find even more patents than we do. Now, if you look at our paper, we do a number of statistical horse races, and we use the evidence from these horse races to make the argument that we do a slightly better job than the USPTO, but I think what I have to concede is that even though we believe we strike a better balance than other papers in the literature, AI patents are challenging to identify from patent text. Ex-ante reasonable approaches can yield very different definitional boundaries, and all approaches are likely to generate some degree of noise. So our ongoing efforts to update our AI patent data through 2024 are leveraging recent advances in LLMs to try and produce an even more precise definition of AI patents, and I'm happy to talk about that ongoing work in the Q&A. Having settled for now on a definition of AI patents, we can use our data to map the flow of AI-related invention over time, and our methodology suggests that AI in patenting has grown very rapidly over time. It's also widely distributed across patent classes, so the USPTO actually has a designated AI patent class, but you can see that the vast majority of AI patents are actually filed in the classes associated with the domain of application, rather than the upstream technology. We also observe that there are a very diverse range of firms that are significantly engaged in AI-related patenting. So there's some concentration in big tech, but you can see that lots more patents collectively are coming out of firms in traditional manufacturing, services, banking. It's really a very, very broad range of firms that are engaging in this kind of invention. Finally, we can use the data in patent documents to locate AI invention in geographic space, and this is the map that results. And so we see some predictable, perhaps, concentration of AI invention in the tech hubs in Seattle, Northern California, Southern California, and New York, but there's also a lot of activity outside of those hubs. But we want to do more than just create cute pictures with patent data. We want to see what impact AI invention is having on the AI inventing firms, and thankfully we can use the USPTO patent to census entity crosswalk to link patents to firm and establishment level measures of employment, revenue per worker, TFP, value added, production worker shares, and even data on the complete distribution of income within the firm from the LEHD. Okay? So to measure the impact of AI invention, we can use firm fixed effects models to measure the within-firm changes that are associated with AI inventions. And we can examine both the extension margin, that is the transition into AI patenting, the extensive margin, and the intensive margin, which is captured by growth in a firm's stock of AI patents. But we can also create groups of non-AI inventing firms to which we can compare the AI inventing firms. And this can be done through the usual propensity score matching techniques at the firm level using firm characteristics such as size, age, 4-digit NAICS code, multinational status, whether the firm has any patents or not, etc. And then we can perform an event study centered around the timing of the first AI patent with a treatment group and a control group to measure whether there are benefits to employment or productivity resulting from AI inventing activity. Okay? Now, this is at the point where I have to say that if there are any labor economists in the room, right, our work is primarily descriptive, and we are not advancing strong claims about causal identification, at least not yet, but we still think these results are interesting and encouraging. So, using our fixed effects models, we find strong evidence that the transition into AI patenting yields an increase in measured labor productivity of 23 to 27%, and an increase of more than 8% in total factor productivity. Now here we're just focusing on manufacturing firms because that's the subset of firms for which we can measure total factor productivity reasonably well. These are large effects, and they're not limited to the extensive margin, that is the transition into patenting and AI. We also find that as the stock of AI patents rises, labor productivity and TFP increase even more. The elasticity for the former is between 10 to 15%, and for the latter, nearly 6%. So again, these are effects that are not just statistically significant, but also quite sizable. Okay? When we use propensity score matching techniques to match AI inventing firms with their closest same industry peer firms that don't generate AI patents, and take an event study approach with this matched sample, we still get strong results. suggesting that the transition into AI patenting is associated with a 14% increase in employment and a 16% increase in labor productivity. Now, the event study approach necessarily focuses only on the extensive margin, but it allows us some additional empirical leverage around omitted variable bias and other inference challenges. So far we see evidence that AI invention boosts revenue per employee and it boosts employment. And the overall, but might AI invention also widen income inequality, right? There was a lot of discussion in the keynote about the effects on income distribution. Now, with our methods, we can only look at the impact of AI invention on the wage distribution within AI inventing firms, so that's a limitation, right? But of course, we know that earlier generations of IT innovation dramatically expanded income inequality, right? The keynote speaker referred to that. Right? And there's real concern about whether AI will continue or even worsen this long-standing trend. So again, focusing only on the impact on the AI inventing firms, not on the impact on AI using firms, we can examine the impact of the transition into AI invention on demand for production workers, right? Which is one way at getting at the high-skill, low-skill dichotomy. But we can also link data on our AI inventing firms to the LEHD, which is a database that allows us to measure essentially the entire income distribution within these firms over time, okay? And so we can measure earnings inequality and its evolution within the AI inventing firms by looking at the familiar 90th percentile to 10th percentile, 90th to 50th, and 50th to 10th income ratios, right? And in principle, we could look at other ratios, we could look at other measures of earnings dispersion. This is what we're doing in this paper, okay? So our bottom line is that in our most stringent regression specifications, we do not see statistically significant effects of AI invention on earnings inequality within the AI inventing firms. The effects on production worker share are generally not robust to the inclusion of firm fixed effects, and the effects on the earnings ratios don't survive in our event study specifications. Right? So if you're an AI booster, right, an AI proponent, like my friend Eric Brynjolfsson, these results are really quite positive, right? We find significant positive effects on productivity and employment that are economically large and no statistically adverse effects on wage inequality, okay? But we're also trying to go beyond what patent data alone can teach us because we're well aware that not all AI inventions are patented. For example, the quantitative hedge fund industry that hires a lot of CMU computer science graduates, right, has been hiring large numbers of elite AI experts from many sources, but that industry generates very few patents. So in contexts like this, how do we find the data trail that reflects firm investment in the use of AI to re-engineer firm products or services or create new ones? So in pursuing these questions, we're inspired by Tanya Babina's work and that of her colleagues, but we take a somewhat different tack. Our aim is to follow the finite number of experts with frontier AI knowledge, right? So maybe this is a somewhat elitist approach, but this is Georgetown University after all. All right, so the basic idea here is that any firm seeking to apply frontier AI technology to a particular problem is going to require a pyramid of AI talent within the firm, right? And you think of the different levels of the pyramid as reflecting different levels of AI skill, right? So at the moment, these high-level software architects, right, the people who have been trained all the way up to the technology frontier, right, people with PhD-level expertise from places like Stanford, MIT, Carnegie Mellon, right, Georgetown too, right, probably. These people are in very short supply, right? My colleagues in computer science know this because even their marginal graduate students are getting industry offers whose salaries dwarf their full professor salaries, which creates some interesting psychological dynamics within the School of Computer Science, right? Because these individuals are in short supply, right, the allocation of these architects across firms, industries, and projects may be especially predictive of firm success in being able to apply frontier AI to business problems. So could we track these high-level architects as they move across the firms that employ them? Right? Well, we think that perhaps we can. And so what we're doing is we're finding leading AI scientists using Elsevier publication data. And we're measuring the direct collaboration between these elite AI scientists and firms using papers that are co-authored with firm scientists and engineers as our empirical indicator of this collaboration. But we can also use faculty websites and other sources to identify the doctoral and postdoctoral students of these elite AI scientists, okay? And we're using Revilio data to trace the movements of their students across organizational boundaries and over time. And then we can link this to census data so that we can directly test the hypothesis that the emergence of a critical mass of frontier AI researchers within a firm leads to increases in output and employment and productivity, or maybe not. Okay? So to make this more concrete, imagine that we could identify Dr. Who, right, who acquires a PhD in machine learning in the 2010s from CMU's School of Computer Science, focusing on image processing, okay? And then Dr. Who moves to Google DeepMind, where he hones his skills in a corporate environment and begins to apply his image analytic skills to diagnostic imaging data. And then he carries these skills further into the healthcare domain by joining Siemens Healthineers division, which is a global leader in AI-driven diagnostic imaging. And then he moves from there to a smaller, newer entrant, Arteris, where he leads a successful effort to create a new suite of products that disrupts the market. Now imagine that we were able to follow all such individuals wherever they went and examine how the output, productivity, and employment of firms that they were employed by changed as they moved. Imagine that we could create a stock of such individuals at a company year level that reflects arrivals and departures, and further imagine that we could use standard empirical methods to measure the effects of that stock on the firms that employed them in terms of output, employment, productivity, and other economic outcomes that we all care about that were discussed in the preceding session. Now, we're not there yet, okay, but we've identified about 2,000 super elite AI scientists whom we dub within our research team the Immortals across 10 domains of AI. We've identified more than 347,000 papers associated with these Immortals, of which about 54,000 are directly co-authored with corporate scientists and engineers. But we've also identified close to 20,000 graduate students, right? And we're starting to track those graduate students across, in this case, the US firms that employ them, because we're trying to match this to census data, okay? Now, I just got an update on the amount of time that I have, right? So I'm not going to, talk about our very preliminary evidence from this part of our study. Instead, I'm going to move directly to preliminary conclusions, right? And here's what they are, at least for my team at this point. We believe that machine learning-based approaches can identify AI-related patents with a pretty high degree of confidence. And we find strong relationships between AI invention and the subsequent labor productivity growth of AI inventing firms. And we also find positive effects of AI invention on employment, right? So they're hiring more workers and their workers are becoming more productive, right? And as you might have noted, our current set of AI patents basically ends in 2018. So we're completely or almost completely missing the impact of recent advances in large language models and generative AI. But hopefully by some point later this fall, certainly by Thanksgiving, that would give me something to be thankful for, we should have updated our patent database all the way up through mid-year 2024. And so we'll be able to capture some of this exciting, more recent wave of innovation. We're also measuring direct collaboration between elite AI scientists and US firms, and we're obtaining data on the movement of their students into industry. And we hope to be able to examine the impact of this elite human capital, if any, on US firm output, employment, and productivity. Now, our census database is necessarily limited to US enterprises, but the methods we're using here could be applied in similar databases all over the world. And with that, I'll conclude ahead of schedule. Thank you very much for your attention.
All right. Now that we resolved the little slide struggle, so let's go ahead. Yeah, my name is Manuel Hoffmann. I'm a postdoctoral researcher at Harvard Business School. This is joint work with Sam Boise and Frank Nagel, also from HBS, and good colleagues from Microsoft and GitHub. First, thank you as the organizers and you everybody for being here. I'm going to talk today about generative AI and distributed work in the context of open source software. All right, so it's a little bit cut off, but I think the main idea we'll see here. The main idea is you can think about individuals. We heard about like high-skilled AI elite scientists just before. Here you can think about similar individuals that are very high-skilled and that exist in our society, but they don't. There are not that many of them, right? Here you can see a comic of all modern digital infrastructure. So this is the world we live in, and there are a couple of dependencies, really very many. And you can see at the bottom there's a piece in the machinery that's a project that has been thanklessly maintained by a random person in Nebraska since 2003. So seems to be the case, at least from this anecdotal evidence here from this comic, that this person is quite important. Take away this little linchpin, is what we call him, right? Then all this machinery may break apart. So it just goes to say that this individual is really important. We have a bunch of those individuals in general. And what we are trying to think about is how technology may help or hinder. We think it may help those individuals to engage in their job a little bit better. All right. This is all a little bit shifted, but yeah, you get the main idea. So we are asking, how does AI adoption change distributed work patterns for linchpin individuals in particular? So we are focusing on maintainers. Think about software developers broadly of open source software projects. So open source software is really basically it's software that is publicly available under a particular license where you can reuse it continuously. And yeah, we are going to focus on those individuals where we have some deeper understanding of those high-skilled linchpin individuals. We are looking at a natural experiment where we focus on GitHub's Copilot, which is offered as a free coding generative AI tool to top maintainers at the discontinuity, where some are receiving it and others will not for free. And what we find when this generative AI is provided for free to those individuals is that we see task reallocation where individuals are engaging more in their core work being coding, and they are engaging less in what we think is project management. So we also see, consistent with what has been stated previously, that lower ability individuals are benefiting a little bit more in this space. So going back to those linchpin individuals. So we have individuals that are super highly skilled, and we think that they are kind of the bottleneck, right? We need to communicate with them. They are doing a lot of the hard work, and a lot of individuals are relying on those linchpin individuals. We think those kind of bottleneck individuals problem is more pronounced in a public good settings. Similar to that, what we can see in the context of open source software, where software is freely available to other individuals, and where we can see that 50% of projects rely just on one single individual, and really a vast majority, around 5% of developers, generate most of the value in this space. So we also think when we're when we're thinking about distributed work, where people work across the globe at different places, that there's a further worsening of the reliance on those linchpin individuals. So if you think about distributed work, you can think about the internet, right? The internet, well, the internet is a fantastic thing in the sense that it has reduced communication costs. So now we all can chat with each other. That's fantastic. But we probably don't all chat with each other. We probably talk to a particular type of people. And some people get substantially more attention than other individuals. And we think that those linchpin individuals are going to be the ones that are receiving most of the attention, and that means they are going to be overburdened potentially more when they're communicating with others. So there's a lot of demand for those individuals. And so you can just think about, of course, the pandemic as just one idea where we have seen remote work arise, where we've seen the idea of distributed work becoming substantially more salient in society. So we think, given that those linchpins are so high in demand, the question becomes, what can we do about it, and what has technology to offer? And for that, we are first splitting the work of individuals into two kind of categories. If you're thinking about high-skilled labor, or generally what individuals are doing in the information economy, we are thinking about them as engaging in core work, or engaging in, you can think about it, non-core work. And in this case, we think about that as kind of managerial work. So for, let's say, for a professor, that might be, your core work might be research, right? But then you have a lot of other things going on where you need to coordinate, you organize a conference, bring all of those people in, and maybe that's not your main part of the work. Maybe you want to focus more on your actual research, and maybe AI could help with that. But the idea is that developers here, in our particular context, face the same kind of, have the same kind of work dichotomy, where they are focusing on coding, and then they have project management, which is really interacting with other individuals and trying to solve problems, fix bugs, think about features that should be implemented. So for those, you need to interact with other individuals, and you need to manage projects in particular. And what they're saying is, well, I'm doing a little bit too much of the project management part, and I'm doing too little, I'm engaged in too little of my core work, right? So could AI now allow us to substitute away from the scarce resource and in essence assist those individuals? So in particular, for open source software programming, AI could relieve developers from repetitive work, substitute advice from other developers. So think about this metaphor of the AI pair programmer that Microsoft is using. You're putting an pair programmer next to you, and that just happens to be the AI, right? It could increase efficiencies overall, increase learning, and reduce collaborative frictions. So we are asking, therefore, how AI changes the nature of distributed work, and in the context of open source software production in particular, where we are wondering how AI changes task allocation, and also whether it could relax the linchpin constraint. So, well, there's a wealth of literature out there. It's growing by the day. Here are just a few. We also have some literature in the space of Copilot, a few experimental studies. You will see another more quasi-experimental study later in the day. But the main idea is, for this paper, that we have seen a lot of work coming out recently that is on the productivity effects of AI. We've also just recently heard that, right, in the prior talk. We heard that in the keynote, how important that is, and that it has, seems to have productivity benefits when we're introducing artificial intelligence. Okay, so what we are trying to do is we're trying to go a little bit beyond the productivity effects, trying to look at the nature of work, and we also contribute to this literature on the impact of AI on the private provision of public goods, which is open source software. We can, due to this natural experiment, we can provide long-term causal evidence from AI in a real-world scenario. And we do this with this natural experiment where some individuals receive generative AI for free and others do not receive it right at the cutoff, that is defined by GitHub. All right, so, well, if you're not familiar with it, well, what is GitHub? Well, GitHub is the hub for collaborative open source software development. It's one of the major platforms of open source software production. Think about open source software as, think about anything that you're touching in the digital world, and now think that basically that has something to do with open source software. By some estimates, around 96% of code, be it proprietary or not, is going to be has some component of open source software in it. So really everybody that is a developer is active in this space. So now, and they are all heavily active, those individuals on GitHub, which was this platform founded in 2008. It has been bought some years ago by Microsoft, but it allows for working on your code, and it provides a time-stamped history of coding. So think about you working on a Google Doc, and when you work on it, maybe you want to go back a couple of days to a version a couple of days earlier because you made a mistake, or you just want to go to a different version. And you can do that easily with Google Docs, right? You just have different versions. So developers do the same thing. They save, they upload the code to the platform, and then they can look at the previous version. So now, because of this biggest platform of open source software in the world, we have very granular information on distributed work with other individuals. So that's people working across the world, and they are engaging in coding, and they're engaging in project management. Right, so what does that look like? Well, here you can see a snapshot of one particular project. In this case, that's called XZ, and at the top left, you see code. So that is the screenshot for where individuals are active for coding. So you can see a couple of folders and files, and that's where that's where you can basically track all of the changes, all of the work that individuals are engaging in when it comes to coding. Our measure is based on this kind of tab. So think about this tab capturing coding. Now, we also can think about project management. Here we have what is called an issues tab. In the issues section of GitHub, the project developers, they are interacting with other individuals. You can ask questions and think about bugs, features, etc. And they're going to come up in this board, and then you can manage them. You can pull in other developers that are developers in the project and ask them to solve those problems if you like. All right, so GitHub has those nice features, but also has created this generative coding AI, which is really based on ChatGPT, which we're all familiar with, right? The generative pre-trained Transformer 3 series in particular was what GitHub is using, and you can think about Copilot really instead of next word prediction. Think about it in terms of next code prediction or code completion. So here is a screenshot of where you sent a tweet, and now the programmer is creating a function header. What happens is Copilot suggests the rest of the code. All right. So In 2022, in the summer of 2022, GitHub has released a general access version of Copilot Generative AI, so you can purchase it, but some people can get it for free. Some of those individuals are what we call top maintainers. We track them over 2 years until the summer of this year. We can continue doing that, and we look into coding and project management in particular. Then we're looking into this program of top maintainers in particular, where GitHub provides individuals with free access that have an internal ranking that is connected to the projects that people work on, and where if you're below a cutoff, you're getting access, and otherwise you don't through this particular channel. Now, the nice benefit, to give you an idea about the validity of this approach, is that we don't think there's any manipulation in this environment. So people cannot just move from the right to the cutoff, to the left to the cutoff to get generative AI in terms of Copilot. Here's a person that is answering a question or is stating GitHub Copilot is available for free to popular open source projects. What GitHub defines as popular open source project is sadly not expressly stated. So people actually don't know how they get their ranking. And so we use the standard RDD approach. For sake of time, I just will give you the idea that we are looking into the relative frequency of coding to overall activity and the relative frequency of project management to overall activity. We have around 6 million observations in this data set. It boils down to around 200,000 when we go close to the cutoff and actually look into our sample. So this is unfortunately a little bit cut off, but I think I'll convey the main idea. Here you can see on the right individuals in the control group that have that use GitHub Copilot, but don't have access through this program. Now you can see that you see a little bit of an uptake. Which is mainly driven by free trials. Now, when people receive Copilot for free and get eligible, you see a large jump in Copilot usage. We see that this transfers at the cutoff to an increase in coding, in the relative frequency of coding, and the drop in the relative frequency of project management. We see this also when we use when we just look at the compliers, we see large increases in coding, large drops in project management. And the idea here being that this is kind of consistent with how we think this Copilot works. You're using Copilot and now you're solving some problems. That means you don't have to interact as much with other individuals to solve problems. You just do that by yourself. And we see that as kind of consistent with the granular effects that we find, where you can see at the bottom here that's push commits. That's the main activities that you can do autonomously. So autonomous activities are going up on coding, and collaborative activities are going down. That's, for example, pull request where you need to interact with other individuals. And for project management, something like bringing in other individuals to solve problems, those measures like assigning other individuals to problems are dropping. So we can trace this effect over 2 years, which is relatively stable over time. We also find that similar with the stories that you've seen before on a bunch of proxies of ability. Here are high ability individuals in orange. They are coding relatively more, but the low ability individuals code even substantially more, which is maybe a sign of learning. And we see the same occurrence in project management, where high ability individuals engage in less project management, but then low ability individuals engage in even less project management than them. All right. So, well, this is here place an emphasis on the nature of work instead of productivity, with the natural experiment in AI adoption with the causal interpretation. For 2 years, in a real-world setting where we find that the core work increases, project management drops, with treatment effects for around 2 years, which seems to be driven by the low ability individuals. This is generative AI, in this case, seems to here be really helpful for the public good of open source software. It kind of changes the nature of work in a distributed work setting. And if you want to extrapolate that a little bit, maybe think about organizations. You could think about the result of project management as somewhere it may lead to flattening of organizational hierarchies. Thank you.
Great, yeah, thanks so much for having me here today. My name's Sam Manning. I'm a senior research fellow at the Center for the Governance of AI, or GovAI. And this is going to be a presentation of some joint work with Pamela Mishkin, Taina Elawandu, and Daniel Rock. The paper is called GPTs are GPTs, an early look at the labor market impact potential of large language models. I will walk through some motivations for why we wanted to do this work in the first place, our approach and methodology, key findings, some validation exercises around those, and then wrap up with some kind of bigger picture takeaways and areas for future work. Cool. All right, so big picture, stepping back, thinking about the motivations for this work in the first place, I think they're rooted in large part in the stated kind of missions of some of the larger AGI companies, AI developers, that include this kind of stated intention to try to develop systems that can outperform humans at most economically valuable work. And I think if we take that seriously and they're successful in this technological endeavor, that implies really a transformative time for workers and for labor markets. And by default, maybe that could go well, I think, but I think there's reason to think that if you step back and think, well, what's the goal for AI development here in terms of its economic impact? My view is it'd be nice if we could have AI lead to accelerated growth, but ensure that that growth is also broadly distributed and leads to shared prosperity. There's probably going to be a role for public policy to play in nudging us towards those outcomes. But in order to inform policy, which I'd love to talk with folks in this room about, we need a basic understanding of the labor market impacts, both observed and projected, that these increasingly capable technologies might bring. So we try to start to build up some evidence on these impacts. We do that kind of through the framing of this bigger picture question of whether or not large language models, like those developed using generative pre-trained transformers, or GPTs, whether they exhibit the properties of the other GPTs, general purpose technologies. And so we asked this question, are GPTs? To do that, we start to look through the economics literature to identify, what are the key properties? There's 3. One, general purpose technologies throughout history have been pervasive. They've affected lots of jobs and aspects of production throughout the economy. The other is that they improve over time. And the third is that they spawn complementary innovations and new technologies. Our research here focuses mostly on this question of pervasiveness and whether or not these tools are spawning complementary innovations, or whether or not they might drive more kind of complementary innovation. And we take as an observed reality, at least for language models, that they have been improving over time. And so we don't shed, we don't have much new evidence about that. Our methodology has something borrowed and something new here. We borrow from some of the previous work that Carl and his colleagues have done, and many others listed up here. There's lots of previous literature that's attempted to estimate both kind of the potential for automation across jobs, but also this broader measure of the overlap between AI and similar technologies capabilities, and the capabilities that workers need to kind of perform various aspects of production and work. What we do is develop a rubric to assess these LLM capabilities. That's kind of most similar to the work of Erik Brynjolfsson, Tom Mitchell and Daniel Rock back in 2018. But instead of their focus that was on machine learning generally, we focused specifically on the capability of GPT-4. This paper initially came out right after GPT-4 was released. And yeah, we build up a rubric to kind of in detail describe these capabilities, provide lots of examples about what they're helpful at and what they're not helpful at, and do this kind of exposure analysis, looking at task data for what workers do in the US, and see where these systems might be relevant. The something new is that we tried to like tune and validate this a prompt to actually just see how well GPT-4 itself could help us with this classification task, and then we compare that to ratings that are provided by folks who are quite expert in kind of like what in the capabilities of these frontier AI systems and what they might be helpful with. We also include an assessment of task exposure, assuming that language models like GPT-4 are integrated with other software that workers use in their jobs. So the types of tools that you currently use, making assumptions about if you could build kind of plugins with GPT-4 to kind of more easily fit into your workflows rather than having to kind of just use a chat interface or something like that. And so this data set is probably familiar to some folks in this room. This is just a screenshot from some of the tasks, the worker data on task descriptions that workers complete in their jobs in the US. This is from the Bureau of Labor Statistics ONET database. There's about 20,000 tasks across 900 or so occupations. That's collected pretty frequently by the Bureau of Labor Statistics. We have these descriptions of what workers do in their jobs, and it's an incredible public good. We take, in this far right column, we take these task descriptions and pass them through this rubric to assess kind of the relevance of GPT-4 and GPT-4-like systems to these task descriptions. In the paper, the actual rubric is like much, it's a couple pages long and has lots of detail about the capabilities of these systems and examples. But here's kind of a high-level overview. We have three main kind of classifications that you could make based on the contents of this task description. The first is this E0 rating, which means there's essentially kind of no relevance of a language model to this task. You're not getting, if you're a worker starting to use this task in your production process, or use this system in your production process, you're not going to get a meaningful productivity gain. It's not going to be super relevant. These are things like physical labor tasks, very complicated tasks that rely on high stakes decision making and things like that. And so this is the first kind of no exposure bucket, E0 rating. The next one here is this E1 classification, where using the described LLM in the rubric via just like a chat interface, a worker can plausibly expect to be able to decrease the time it takes to complete this task by at least half, while holding their quality constant. So that's a doubling of productivity. And then the next level up is this E2 exposure, which is where, well, if I'm a worker completing this task, if I need to use just a chat interface, I might not be able to get a doubling of productivity there. That's pretty big. But if it were already integrated into the software I was already using for this particular use case, say it's a legal research tool or a Copilot or something like that, then plausibly I could get a meaningful productivity boost here. So there's some need for some complementary software integration to get this large productivity boost on a task. And so those are kind of our three core classifications. We had a team of kind of folks quite expert in these LLM capabilities and outputs, try to assess these task descriptions, and then also pass these task descriptions through the GPT-4 API. And this isn't really a core finding, but just methodologically, the ratings were quite similar. So helpful to see that if you are cost constrained as a researcher or something like that, you can get some help perhaps in certain situations by using these models to help with text classification tasks. And then in terms of findings, we show that based on this analysis, on average, 14% of tasks within a given occupation are exposed to this doubling of productivity, this potential, big productivity gain from just using a chat interface alone. This is, within a randomly sampled occupation. This is the average. And then we have a couple other kind of occupation level measures that we use. So the first one I just mentioned is just the share of tasks that are classified in this E1 level. It's at 14%. And then the E1 plus E2 is this, the share of E1 plus the share of these tasks that kind of need these additional software complements to unlock this, potential for productivity gain. And then what we did in between is just kind of, if you think about how the software development works in the real world, there's lots of costs and bottlenecks on creating these additional innovations and software complements. And so to account for that we might not actually, get this full software, integration where GPT-4 and similar systems are underlying lots of applications you use, we just scaled down this E2 factor by a half. And so this is an intermediate measure here of this E1 plus half of E2. These are kind of the three core occupation level exposure measures that we use. The story from this is that the extent to which the task composition of different work is exposed to potential productivity gains depends a lot on how much we're able to integrate these language models and their capabilities into other software systems that we can easily use and that reduces the frictions for us to be able to work with them seamlessly in our jobs. And now zooming out to the entire kind of US labor market, zooming out across the economy, this chart shows on the y-axis the share of jobs, the percent of occupations. And then on the x-axis, it gives you the percent of that worker's tasks that are exposed at these different levels. And so if you want to look at that intermediate measure, for example, that E1 times half of E2, or plus half of E2, that's these little triangle charts. The human ratings and the GPT-4 ratings are there. And if you use that, it gives you this finding that roughly 80% of workers have at least 10% of their tasks exposed to these LLMs with some intermediate level of software integration. So not just using a chat interface, but some other, some integration with things you use in your job. And approximately a fifth, 19% of workers in the US have about half or more of their tasks exposed to these potential productivity gains. Again, the story here being that widespread exposure, even if you just look at the E1 ratings via chat interface, but that these productivity gains, this exposure, this relevance to work can really be boosted with additional software integrations where you go up to these square line, these kind of squares, which show kind of much higher share of work being affected if you're able to do more complementary software innovation. And then looking across the income distribution, Carl pointed this out in his talk earlier, that we have wages on the x-axis here and the share of work tasks exposed on the y. Here we see that the percent of your work tasks, your work composition that's exposed to these language models, peaks for jobs that are earning around $90,000 a year in the US, and it remains quite high, well into kind of six-figure salary jobs, but is much lower for occupations earning less, $30,000, $40,000 a year. And so, we have these findings from experimental studies. Oh, okay, great. Great, I'll move along just slightly quicker pace. Great, and then when we look at job groups, so kind of categories of occupations, and see who's more exposed and who's not, we find that, scientists, researchers, technologists are the ones who are most exposed to these productivity gains. Potentially, exciting if you're, hoping that AI can drive lots of innovation and drive lots of new research and development and product development. These are the most R&D intensive occupation categories in the US. And so hopefully, this is a place where lots of new complementary innovations could be spawned from these technologies. So to date, what I've described is a lot of analysis with secondary data, and we have this rubric that you can make small changes to, and it really impacts your results. And we haven't deployed these systems experimentally and observed productivity impacts. We're making some claims about general relevance of these systems, but it would be nice to better empirically measure it. What we do to try to validate and see how well these assessments are mapping onto workers' experiences is ran a survey with ChatGPT users and said, do you use ChatGPT to help you with work tasks? For those who said yes, we asked them, okay, great, can you give us 3 examples of tasks that you've recently used ChatGPT to help you with? These are some of the occupations that folks had, lots of engineers and game developers, students, teachers, writers, managers, entrepreneurs, and they responded with their tasks. We took those tasks, got the embeddings for them, the text embeddings, and compared them to the embeddings for these ONET tasks that we previously passed through these rubrics and graded to see, are people telling us that they're doing tasks that we are rating as exposed, or are we missing something and saying, hey, all these people are using these tasks, using these tools for things that we didn't actually rate as relevant, LLMs to be relevant for. Here are some examples of the tasks that people people reported. So again, this is mapping their self-reported answers to the most similar ONET tasks. Things like researching new software design concepts, composing and editing screenwriting scripts, helping your children with homework for teachers, many other things. And what we found is about 62% of the self-reported tasks, people said, I use this for my work. We marked as this E1 rating, direct kind of relevance from just a chat interface. About 35% were marked as this E2, so you need some additional kind of software, but people are still kind of using it for these tasks. And then only 3% were marked as E0, so where we totally missed the boat. This is just a visual kind of representation of that, where we don't want to see these black circles, which are the user-reported tasks. We want to see them not over the gray E0 tasks in this embedding space, and we want to see them over the blue and red, where we marked E1 and E0. So one validation of this. I mentioned this, so most of that work's been focused on on this question of pervasiveness for general purpose technologies. But kind of highlighting this point that to unlock all these productivity gains, you need to integrate these LLMs with other software. You need to build new innovations to really get the most out of these systems. We tried to do some exploratory work, seeing well, is this happening? Can we observe this happening in any way? And which seems to be a theme of the day, we use some GitHub data to look at the kind of repositories on publicly available kind of code repositories on GitHub that we're building with LLM APIs, so before ChatGPT's release. We looked, if they mentioned Bard or GPT-3, these types of things. And we kind of just mapped out how many forks, how much are these repositories being forked, which means basically you're copying this repository and then you're building new stuff with it. You're doing something else separately with it. And you can see this incredible boost after ChatGPT is launched, where these systems, all of a sudden, we have this shock to how usable the API is, how much these systems are following our instructions, and how helpful they are. And we see, this incredible boost where more people are forking these repositories and doing new things. And it's at least one sign of this kind of complementary innovation that complements what we see in the economy, where we have all these products and services and startups being built around these systems as well. Great, and so I'll wrap with just some key takeaways here. We've generated some initial evidence that LLMs have some of these key properties of general purpose technologies. This pervasiveness, they're clearly improving, and some evidence that they're spawning complementary innovations. What this means for us in practice when we're trying to inform decisions is that the equilibrium effects of general purpose technologies are really hard to forecast, right? We talked earlier about if you were trying to forecast the labor market impacts from electricity when it was first kind of early on in its development, you just wouldn't be able to do it. It's incredibly difficult. And so I think it requires us to be humble in trying to forecast, labor demand impacts and wages and impacts and things like that, but also can spark us to try to, be more creative here and do more, maybe work hard to try to come up with creative methodological approaches to answer some of those questions too, given the challenge. We see broad exposure of current day, present occupations and work to these language model capabilities, but it's clearly centered on more higher wage work in the US. We don't find, and we don't really study whether or not this exposure measure translates one-to-one to labor automation outcomes. So I think that's not a finding from our paper that we're going to 80% of workers are going to automate away 10% of their tasks. It's this potential relevance and productivity gain is there. And for that reason, there's reason to expect many jobs to change, the task composition of jobs to evolve, and for new jobs to emerge as we have these new innovations and integrations. But again, equilibrium effects are going to be difficult to forecast with too much foresight. And so for future research, I think there's still this open question where we don't have a ton of empirical experimental evidence about the marginal impacts that these software integrations have. So in my view and in my work, I can kind of see that building tooling and scaffolding around these models does have a meaningful impact for productivity, but we don't have good empirical measures of that yet. We have a number of experiments with kind of these base models, but it's unclear how much these additional use case specific applications are driving additional productivity gains. And at the same time, there's limited evaluations in real world work settings as well, which seem essential to kind of figure out how are all the complexities of adopting this new technology going to wash out and work out with workers. And then, just to wrap, given the kind of broad relevance across the economy here, more work trying to figure out policy options to ease some of this worker disruption and ensure that productivity gains can be widespread seems essential and something that I'd be excited to talk with you all about as well. So thanks very much.
So thank you for this excellent set of presentations. I'm sure we will have a number of excellent questions to match them as well. If you have a question, please do raise your hand. If you prefer someone in particular to answer it, please direct your question accordingly. And so we have roughly 20 minutes, I think, so we'll look forward to a fruitful conversation. Any hands up? Over there in the middle.
Hi, my name is Bill Hayworth, and I'm a senior advisor at the IFC. I guess my question is to the whole panel, because as I listen to this discussion, one of the things that is sort of making me curious is the idea that artificial intelligence can form hypotheses and then test those hypotheses. And on the basis of the test, confirm or reject the hypotheses. That process seems to be fairly basic in one way, and it seems like some of these large language models are kind of capable of doing that. And if that's true, then that almost implies to me that they're thinking, or they think as well as I can, right? Because half of what I do in life is form hypotheses and figure out how to test it, right? Confirm it, and then move on to the next hypothesis. Is that happening? Do we see that happening? And does that change any of your projections on how that would affect jobs? Thank you.
That's an excellent question. Anybody who's keen on giving it a go?
Happy to give it a shot. Yeah, I mean, so I know there's a group of researchers that are focusing specifically on this question. So Senthil Mullainathan has some work that's exploring kind of AI as a tool for hypothesis generation. And then there's a whole other set of researchers, John Horton and Ben Manning, no relation, at MIT who have done some work to try to automate this process, not the hypothesis generation part, but everything else related to social science. And I guess my understanding of that at the moment is that it gives you these meaningful productivity and discovery boosts. I'm not sure I would go as far to say, as a non-expert on it, but I'm not sure I would go as far to say that this is automating the process of social science research quite yet. But I think there are steps in that direction, yeah, I agree with you. I mean, even in my work too, I think like a lot of what I'm doing is creating hypotheses and doing things, and also just doing pattern recognition in lots of ways. And these systems are getting better and better at that. And so it's a type of thing worth monitoring, and yeah, and that will have large spillovers.
Further questions from the audience? Over there, lady in the middle.
Hi, Jeffrey McNerney. I'm an MBA student here. I had a question, I guess, specifically for Dr. Brandstetter, but as you start looking at the impact of LLMs, GPT, in a very different paradigm of kind of out-of-the-box, off-the-shelf models and systems that companies are adopting versus creating knowledge centers of PhDs and patent holders, do you plan to try and capture that data as well? And then I guess question for the rest of the panel, since your work is focused on those types of technologies, do you see it as a meaningful difference in how to evaluate the impact of AI on productivity and work when you're using these co-pilot systems, complementary products, rather than developing in-house models?
Yeah, so that's a great question, and I think it's a really important one. What the entire research community is struggling with is how would you actually measure, right, the utilization of an existing AI product or a kind of AI as a service. And the Census Bureau has really tried, right? They've conducted some really valiant efforts to survey large, I think plausibly representative samples of US enterprises on their AI use. But this is really hard, right? So first of all, think of who fills out that survey, right? It's probably not the CEO or the CTO, it's more likely the summer intern, right? But secondly, I think a huge number of US enterprises are at least starting to use AI, but the AI is actually bundled in other software services that they're purchasing over the cloud. And I think at the moment, the current survey instruments really don't get at that, right? So, the small, fried chicken chain in southeastern Kentucky gets the survey. Are we using AI? No, we're not using AI. But, they're recruiting workers using, Indeed. They're doing analytics on their website using, Google Analytics. I mean, there are a lot of ways in which they are using AI. And so I think, we've got to, keep on working with these survey instruments to try and get at that indirect use. And I think it could be a potentially big deal. So I hope that addresses your question.
Yeah, it would be fascinating to have a control group of companies who are developing in-house models versus using these off-the-shelf to see how those...
Yeah, but those are going to be really different companies, right? So that really would be, I think, comparing apples and oranges, which statistically is a hazardous thing to attempt.
Daniel, Sam, do you want to come in on this as well?
Yeah, I think it's very challenging to really measure that. It reminds me a little bit of the work that we are doing on what we call the census of open source software, and probably it contains a little bit of AI packages. But yeah, particularly cloud usage, we don't have that at all. You have to collaborate with all of those big companies, with Google, Amazon, etc., right, to even potentially get a glimpse, which is very challenging. So we, and then, like this in-house question, it's, even when you have some measures, we try to do this by looking into like open source software, but then software composition analysis firms, which are really just looking at other companies that potentially merge. So they want to look at the license compliance, and through that one can then understand what kind of code they are using, what kind of software they are using. but that is obviously also just a selected set of firms. So yeah, it would be great to get a better understanding of like a more like a broader method of that. But agreed, it's an important question.
Yeah. So two things might come to mind for me in terms of like driving this distinction between whether or not you're a company and you want to rely on a foundation model or you want to build your own thing. One is you want to get like some additional use case specific capability boost, right? Like you want to build this like legal research tool that has a better set of capabilities for this use case. It can do more fact checking and citations. It has this back end prompting to kind of check things and boost this reliability up. And that seems increasingly important, to unlock these productivity gains, like to have these use case specific tools. The other trade-off, the other thing that I think is going to become increasingly important here is this, these systems are really quite capable and lots of different tasks, but usually for them to be useful, you need to give them lots of data, lots of context about your workflow and your situation. And the easiest way to do that would be to just plug them into all the digital tools that you're using. Customer data, internal, proprietary information. There's like big trade-offs there to work through around privacy and data security. And I think right now it seems like, lots of firms were like getting used to how this is going to work, and it seems rational for firms to just be like unsure about how to manage that when they're trying to, and therefore maybe lean you towards building your own thing. So yeah, some thoughts on that.
Great. Lady in the middle over there.
Thank you. My name is Hillary Johnson, and I'm from the World Bank. I had two questions. First, for the first speaker, I was wondering, with the patent data that you're using, can you do any kind of disaggregation by type of AI or kind of use and how that may alter the labor productivity gains? And my second question, it really could be for anyone, but probably maybe for the third speaker. There's a fantastic paper, I think it's really interesting anyway, called AI is Bullshit by Townsend, Hicks, Humphreys, and Slater. And in that article, they talk about a very scientific definition of bullshit, and explain how basically AI is bullshit because it's agnostic about what is truth. And so my question is, when thinking about the tasks that are subject to, use of AI, right? To what extent should that be taken into account? Is it taken into account? Are there new tasks generated? Because if you're, say, outsourcing a literature review to ChatGPT, chances are you're going to end up with some fake papers in there and things because it's really just, looking at combinations of words that look good together, right? And so, there's going to be new tasks and new time spent to verify the outputs of LLMs if you're going to do it responsibly, right? And so to what extent can that mitigate the productivity gains? And maybe what would need to happen for you to still reap the productivity gains without those downsides?
Yeah, so I'm happy to take the first question. We have attempted to take a look at our AI patents and assign them to sort of different AI technologies. And when we first attempted this, our hypothesis was that the composition of AI has really changed over the 90s and the 2000s and the 2010s when the level of patenting has really ramped up. The short answer of what we found is that actually it appears that things are a lot more stable than we thought, right? But again, we're disaggregating our AI patents on the basis of the nature of AI technology that's being deployed, not the, the industry of use or the domain of application. We could also do that. We just haven't. And as for the bullshit questions, I'll leave those to my fellow panelists.
So on the second question, I think this is definitely true. I actually see some of Manuel's work, like, you guys make this, you have this finding that there's reduced management in this, coding workflow and more coding activity. But in some sense, I guess, at a fine-grained level, these coders are managing the outputs of GitHub Copilot, right? You're prompting a system, you're getting some output, and you need to do this. In some sense, you need to still be involved to assess whether or not this is the output you want, whether it's sufficiently reliable for you to move to the next step. And so in my mind, that could be classified as a production activity or also just a management activity. And while we're in this kind of phase of systems needing this human kind of bookending on the front end of the task to prompt the system and on the back end to verify things, then there's going to be, I think it makes sense that there might be these increasing returns to that skill, to management skills, to being able to decipher, critically evaluate, is this tool providing a reliable enough output for me to use it? And that will limit the productivity gains from these systems. I think we're still pretty early on in the development of the capabilities of these tools, and also, especially in the development of all the complementary software that can channel their capabilities towards specific use cases that they're suited for. And as that progresses, I'd imagine that reliability, at least in some domains, will go up. But it's up in the air to see. It seems far off a bit to think that those reliability issues will be totally solved, and we'll just have this fully unleashed thing. But
I think we have time for one very quick question. Lady over there.
Ana Cusolito from the World Bank. I have a question for the first speaker. I am wondering whether you have measured the differential effect of knowledge spillovers related to AI innovations vis-a-vis non-AI related innovations, because that will give us a sense of how easily this knowledge is diffused, and also shed a little bit of light on the role of public policies for internalizing the positive externalities that AI actually may cause, if any. Thank you.
Yeah, so I guess one immediate response is we haven't specifically looked at that, right? I mean, we're looking at the impact of AI invention on the AI inventing firms, right? I mean, the notion of knowledge spillover is, to what extent would these AI inventions drive greater productivity elsewhere, right? And for that to happen, I think you'd really have to, have data on the usage of AI, right? In a way that might increase, productivity in other domains. I mean, I think there's a lot of hope, for instance, in pharmaceuticals, right? That, the use of these AI tools will actually speed up the pharmaceutical development process, and that could have first-order implications for human well-being. Or you could imagine that, AI becomes a useful tool in other domains of R&D, right? It helps partially automate the process of hypothesis generation and testing, and that improves our research productivity elsewhere. I mean, I very much hope that these spillovers eventually emerge, because most recent data on the diminishing returns to R&D effort in the absence of, a lot of help from AI are pretty daunting, right? And suggest that we're, in for an endless productivity slowdown, with no help in sight. So I very much hope that they emerge, but I can't say that our current research really points to, the existence of these strong spillovers yet. Definitely something to work on.
And on that cheerful note, I think our speakers deserve or have earned their coffee. So, okay. Running.
So thank you very much to everyone in the audience. We're now going to have a 15-minute coffee break, and then we're going to change things up a bit. Where we started off with leading academics, we're next going to go to leading industry experts after our coffee break to hear real-time use cases of AI applications within firms. Thank you very much.